In this lesson, we're going to talk about motional EMF and induced currents. So we've talked about how a current can create a magnetic field. If I have a current of a straight wire, it creates a magnetic field that's in a circular pattern around that wire. But can a magnetic field create a current? This is something that people were trying to investigate, and Michael Faraday decided he was going to set up a circuit like this. He has a circuit here with a battery, and then the wire goes around a metal loop. Then when he closes the circuit, it's going to create a magnetic field through this loop. What he wanted to see was, would it create a current in this other loop, which is not connected? This is a whole separate circuit. Would he create a current there? What he found was it would create a current in this circuit for just a very tiny moment, right when he turned off or turned on this first circuit. So his hypothesis was that a changing magnetic field would create a current. It wasn't a continuous current, it was just momentary while there was a magnetic field being created or a magnetic field being stopped. So Faraday found that there is a current in the coil if and only if the magnetic field passing through the coil is changing. So he had a couple of other experiments that will show this. We have a complete circuit with a coil and another circuit that is below it with a coil. And when you open or close this switch, you create a starting or closing of or beginning or ending of a magnetic field that goes through this coil, and we will momentarily have a current in this circuit. We could also take a simple circuit with a coil and put a permanent magnet into the coil, push it in or out of the coil, and when that happens, we will get a current. And finally, we can have a permanent magnet around the coil, and this permanent magnet, if you push or pull the coil into or out of the magnet, you will get a current in that circuit. So the current created by the changing magnetic field is a new kind of current. It's called an induced current. An induced current is not caused by a battery. It's considered a whole new way to create a current from a changing magnetic field. This is a form of electromagnetic induction. Electromagnetic induction is when we create an EMF or electromotive force across a conductor by exposing it to a changing magnetic field. So let's consider a conductor. It's going to be a length L, and we have a magnetic field, and you can see it's going into the page. We're going to move this conductor along the velocity vector to the right, and we're going to see what happens in the magnetic field. Now, if we're just moving it, you know that our right-hand rule will tell us, remember, V, B, F. So our thumb is going to follow the V, our pointer finger will go into the page, and will result in a force on any charges in the conductor that goes in the upward direction. So after a while, if we continue moving it to the right, that force will cause positive charges to build up in the top of the conductor, and it will leave negative charges on the bottom. Well, a separation of charges is also going to result in an electric field. So an electric field is when we have separated charges, and an electric field will go from the positive charges to the negative charges. So now what we end up with is as we continue to move this conductor, we have a magnetic force, which we call FB, pushing charges upward. And we have an electric force. Because of the buildup of positive and negative charges, our electric force is going to push the charges downward. So we now have two forces, a magnetic force going up and an electric force going down. So the electric force is going to be equal in magnitude to the magnetic force. So our electric force, if you go back to your equations for electricity, it's equal to charge times the electric field. And that's equal to our magnetic force, which we defined as V, Q times V times B, because we're at 90 degrees, so we can ignore the theta. The magnetic force on the charge carriers moving in a conductor will create the electric field, which is V times B. Because if you look at these two equations, if QE equals QVB, then that means the electric field created equals the velocity times the magnetic field. So, since the electric field that's now created in our conductor is equal to the velocity times the magnetic field, we're going to go back and remember that the potential difference across, if I have separated charges and an electric field, the potential difference divided by the distance between those charges is equal to our electric field. This is an equation from the AP Physics 2 equation sheet. In this case, our delta R is going to be the length of the conductor. So the result is that we now have an electric potential that's equal to the electric field times delta R, and that potential equals the electric field, which I've said is V times B, times delta R, which in this case is L. So this equation is also on your AP Physics 2 equation sheet. This says the potential difference across a conductor that's moving through a constant magnetic field is equal to the velocity of the conductor times the length of the conductor times the strength of the magnetic field. So what we've created is called motional EMF. So a battery has a chemical EMF. That's the potential difference in a battery. When we move a conductor, we're creating something that's called motional EMF. And its equation is that the EMF equals the velocity of the conductor times the length of the conductor times the magnetic field. So if I move a conductor through a magnetic field, I'm going to create a potential difference that we call motional EMF that's equal to VLB. This equation is on your Physics 2 equation sheet. So let's see an example of just what it looks like. Let's say we have a square conductor moving through a uniform magnetic field. Which of these figures shows the correct charge distribution on the conductor? You're going to use your right-hand rule to figure out which direction the charges will feel a force. So your thumb should point in the direction of V, your first finger should point in the direction of the magnetic field, and you should get a force that's going to the right. A force going to the right is going to make your positive charges go to the right. So the answer is E. Positive charges have a force pushing them to the right. So now we've created motional EMF. We now have an electric field across the conductor and a potential difference across the conductor. So now we're going to make it a little bit more complicated. Besides just moving a conductor through a magnetic field, let's say we have a fixed rail. This orange bar is fixed in place. It's not moving. It's in a uniform magnetic field, and I'm going to touch a conductor to the ends of this rail, and I'm going to slide it down. So what I have created is the same kind of conductor moving, but now it's connected to a conductive rail. This rail is basically going to create a circuit for me. So I'm going to use the ideas of induced EMF and see how to create a current for a conductor moving in an electric field. So as it moves, we have a force that pushes up, so we build up positive charge here and negative charge down here. But now, instead of being stuck at the top of the conductor, those charges can continue to move in a circuit, and it creates a current that flows around. So we move the conductor to the right in the magnetic field. Instead of stopping at the top of the conductor, the positive charges continue to move around the circuit, and this creates what's called an induced current. This induced current is counterclockwise. You can see the direction that it turns. So now that we have a current that's produced, we're also going to have a magnetic force. If you remember, anytime we have a current, it will create its own magnetic force. So we have our current going counterclockwise, and we use our right-hand rule. We follow our thumb. We do I, B, F. I goes the direction of the current. B is into the paper, the direction of the magnetic field, and we end up with a force that goes to the left. This is the magnetic force that's the result of the current moving. We also call this sometimes the magnetic drag, and it's because it's slowing down the motion of our conductor. So the magnetic force or magnetic drag is going to stop the conductor from moving to the right because we have a pull that's pulling against us. So in order to keep our conductor moving at its constant velocity v, we're going to have to apply a pull force. We have to apply a pull force to, oh, this is incorrect. We have to apply a pull force to the right, which is equal, it's not to the left, it's to the right, equal to the magnetic force to the left to keep the conductor moving at a constant velocity. So our magnetic pull force is now equal to our magnetic drag force. And our magnetic drag force is just the force from the current, which is I times L times B. So we also are going to look at one last thing in an induced current, and that is getting an induced current from a generator. A generator is a device that can convert our mechanical energy, or a spinning coil, into electrical energy. This should look familiar. This is the opposite of what we had with a magnet. A magnet used a magnetic field to turn a coil. Now we have a turning coil that we're going to use to create a current. So the coil is rotated either by a hand crank, or there may be a combustion engine, or there may be steam, depending on the type of generator that we have. So we have a coil that is rotating in a magnetic field, and as the coil is rotating, it's going to have a changing magnetic field. So we have steam, let's say we have steam turning the coil around. The coil is turning. As it's turning, it experiences a changing magnetic field because its angle changes. As it has a changing magnetic field, it's going to produce a current. The current is actually going to be an AC current. It's going to be positive and negative and positive and negative because the direction of the coil is going to flip. This is a backward motor. The changing magnetic field induces a current in the wire. We can use that current to generate electricity.